Continuing our investigation of series circuits, next we're going to look at how voltage works in a series environment. So look at this problem here. I have a simple series circuit with two resistors. I know my resistances. I don't know my total resistance, but that's pretty easy to find. But I don't know my starting voltage. How can I figure that out? Well, the thing to keep in mind about voltage is to remember that it is electrical potential energy. As we move our charge through this situation, we're going to lose energy. We can think of this situation like I have a multi-step hill. And I have a ball that has a certain initial velocity, something greater than 1. It's going to use up a certain amount of its initial kinetic energy to get up the first hill. After that, it's only going to have a certain amount left, and it's going to use the rest of it to get up the second hill. Resistors are just like that. In an electrical circuit, my resistors basically act as these little hills that are going to use up some of that energy. Now, how much energy do they use up? Well, quite simply, they use up the same proportion. Each resistor will use up a certain percentage of the total voltage equivalent to the percentage of their resistance. What does that mean? Let's take a look at that. So first we need our total resistance. That's going to be R1 plus R2. Remember, total resistance is equal to the addition of our individual resistors in a series circuit. So we take R1 plus R2, that's 200 plus 300, that gives us 500 ohms. Alright? So now, what percentage of R1 is the total resistance? What I mean by that is R1 divided by RT. What does that equal? That's going to be a percentage. Is going to be 0.4. So 40% of my resistance is in R1, which means R1 is going to use up 40% of the total voltage. So my voltage across R1 is 10 volts. So I can use that to figure out what the total voltage must be, because 10 volts is going to be 40% of the total voltage. How do I figure that out? Well, I'm going to set up the same ratio. It basically works like this. I say R1 over our total is going to be equal to the voltage at R1 divided by the voltage total. So now I know the resistance of R1, I know the total resistance, and I know the voltage across R1. So I'm going to set up that proportionality, and then I'm just going to solve for it. So in the same way, I get this over here, let's cross that out, it's going to be 0.4 equals VR1 over VT. In order to solve that, I just take my total voltage is going to be equal to VR1 divided by 0.4. So I take 10 divided by 0.4, and that will tell me my total voltage. That equals 25. So my voltage, V1, my total voltage is 25 volts. All right, now I can use that to find the current in my circuit. So I'm going to take 25 volts using Ohm's law. It's going to be 25 equals 500 ohms times I. So divide both sides by 500. And I get a current equal to 50 milliamps. There we go. So, a rule for voltage in a series circuit is going to be very similar to our rule for resistance. So my total voltage is going to be equal to my voltage at R1 plus my voltage at R2 plus my voltage at R3, and so on. So, no matter how many resistors I have, the total between all of them is going to be my total voltage. Finally, let's look at current in a series circuit, because this is also going to follow certain rules. As my voltage goes through and gets used up, all of my charge is getting used up. It's all moving. It's all moving through here. And just like we looked at the conservation of energy, in electrodynamics, we have the conservation of charge. So let's write that down. That means charge is not going to be created or destroyed, it's just going to move around. So, as I move through here, all of my charge has to move through there. Well, if I've got a piece of charge moving at a certain rate here, it's going to have to move at the same rate down here. So throughout the entire circuit of a series circuit, my current has to be the same. So my total current in a series circuit is going to be equal to the current at each point. And so on. So I've got two resistors here, and I know my total current is 20 milliamps. Well, in order to figure this out, the thing to keep in mind is that it's going to be the same at each resistor. So the current at R1 is going to be 20 milliamps. The current at R2 is going to be 20 milliamps. So now I can very easily find the voltage at each of these points. All right, so 20 milliamps, 100 ohms. I'm going to take trusty Ohm's law, and in order to figure out the voltage at R1, I'm going to take 100 times 20. Well, not times 20, actually, times 0.02. Because remember, this is milliamps, and I need to convert it into amps. So 0.02 times 100 is going to be equal to 2 volts. So my voltage at R1 is 2 volts. Now at R2, I should be able to just do that in my head because it's double R1. So the same thing should be true down here, so it should come out to 4 volts. But let's do the math anyway. So I'm going to have a second round of Ohm's law. And that's going to be that 0.02 amps. Oop, that's nuts. That's a squiggly line. That's nothing. And 0.02 times 200 is going to be 4 volts. Now, my total resistance is going to be the addition between R1 and R2. Remember, total resistance is R1 plus R2, so R3, and so on. And total voltage is going to be equal to V1 plus V2 plus V3, and so on. Okay. So, total resistance, 100 plus 200 is 300 ohms. Total voltage, 2 plus 4 is going to be 6 volts. And now we can check that. I should be able to take Ohm's law one last time and say my total voltage of 6 divided by my total resistance of 300 should be equal to my current of 20 milliamps. Let's punch that into our calculators and make sure. And it is 20 milliamps. So that's what's really nice when doing circuit analysis, is you really have all of these rules that circle back in on themselves, so you have multiple ways to check to make sure that you got the same answer. So that covers it for all of our rules for circuit analysis in a series circuit. So our total current is equal to the individual currents at each resistor. Our total resistance is equal to the resistors at each point, and our total voltage is equal to the total of all the voltages in each resistor.